Things. So you're going to have the second quiz tomorrow. You need to know 5 of the strong acids, their formulas. I know, I bumped it down to 5. That was nice. Okay. All right. Only need to know 5. Formulas and names. You need to make sure that you understand what happened in that lab in terms of how you calculated the molarity of that base. So remember, you started with some number of grams of KHP, and I will give you the molar mass of KHP. And you remember, you changed that into moles of KHP, and then, because that's a 1-to-1 ratio, that became moles of sodium hydroxide. And then you divided that by the volume of your sodium hydroxide, because that's what you were trying to find is molarity. Okay? So make sure that you understand that process. Like, oh, it's a 1-to-1 ratio. Boom. You know the mass of KHP, find the moles of KHP, and the moles of sodium hydroxide. Divide that by the volume. There's going to be a KB problem. Okay? So, and this is relevant to what's going to happen on this assignment from yesterday. So remember, on a KB problem, you're going to have some base, okay? And that's going to react with water, and you're going to reform an acid, and you're going to generate hydroxide ions. So remember, on this rice chart, okay, here's what's going to be different. On this, that's going to be some molarity, maybe 0.2, whatever it is I give you. That's going to be 0, that's going to be 0. You're going to go minus x, plus x, plus x. That's going to be 0.2x. So the biggest thing you have to remember is that when you do that KB, that's going to be x squared divided by 0.2. So when you find x, you're finding your hydroxide ion concentration. Take the negative log of that, that's your POH. From there, subtract that from 14 and get your pH. Okay? So that's different from Ka values where you're finding your hydronium ion concentration. So that's going to be the biggest thing. And like I said, tomorrow I'll do a demonstration tomorrow before the quiz to kind of show you more of a visual of how that works. I'll use ammonia, which is kind of the quintessential like weak base, and how that interacts with water. So we'll do a demo with that tomorrow before I actually give you the quiz, so you kind of see how that plays out and the impact that has. Okay, so the assignment from yesterday. So I want to make sure everybody's clear on the difference between what happens when you have a strong acid and a strong base versus what happens when you have a weak acid and a weak base. So if you look on number 1, okay, you're going to mix, if you were to write out the full-blown equation, you would have hydrochloric acid and sodium hydroxide, and you're going to get water and salt. Okay, so you're basically making salt water out of this reaction. So that's the full-blown one. In reality, the only thing that we care about in terms of the net ionic is your hydrogen plus your OH making water. Okay, this is the only one that really we care about. And here's the reason why. We don't care about the chloride ion. Okay, and here's the most important thing that you need to understand. That chloride ion is in that solution. Okay, it's there. And it's attracted to the water, because the water molecule is polar. Okay, so that chloride ion is going to be attracted to the positive end of that water molecule. But it's just an electrostatic attraction because you're oppositely charged. That chlorine isn't going to go up to the water and go, give me your proton, because it doesn't have enough oomph to do it. It doesn't have enough moxie. Okay? It's attracted to it, but it's not going to take a proton. And we know that because the chloride ion is the conjugate base off of hydrochloric acid. So this is a logic problem. hydrochloric acid is a strong acid. That means that it ionizes. Oh, okay. Because it ionizes, that means that the hydrogen and the chlorine basically really don't, they're attracted to each other, but they're just friends, okay? They like each other, but not enough to like really hang out. It's like, it's an acquaintance, all right? And we check on each other on Facebook or whatever social media that you use. But that's about it. We're not going to hang out. So the chlorine is there, but it's not going to interact with the water to reform hydrochloric acid, because here's the dichotomy. The stronger the acid is, the weaker the conjugate base. So hydrochloric acid is a very strong acid because it has an exceptionally weak conjugate base. Okay? So the chlorine is there, we just don't care about it because it's not going to make a secondary reaction. So if you look at what's going to happen, if you got, and I would work in millimoles, you can work in moles, whatever that you want to do. But here's what you cannot do, and listen to me very carefully. When you have any neutralization reaction between an acid and a base, you are forbidden to work in molarity. Okay? You can work in moles, you can work in millimoles, because it's quantities that are going to be consumed, not molarities that are going to be consumed. Okay? So when I did this, I worked in millimoles, and I said, okay, hey, I got 2 millimoles of my acid. I've got 1.5 millimoles of my base, okay, and that's all I'm really going to worry about. So all of that's going to get consumed, minus 1.5. So that tells me that I have 1/2 of a millimole of hydronium ions left over. Now, is that my hydronium ion concentration? No. All that tells me is that that's how many millimoles of acid that I have left over. So at this point, when you find that pH, you need to take the negative log of your hydronium ion concentration. That is not your hydronium ion concentration. But can you use that to find your hydronium ion concentration? All day long. So Gracie, what are you going to do?
Divide by the amount.
Yeah, divide by the total volume, which is what, 35 milliliters? And you get 0.014. That's your hydronium ion concentration. Take the negative log of that. Boom, there you go. So your pH on number 1 should be a little bit less than 2. Anytime you have pHs, remember, the rules of significant digit gets wonky when you're dealing with pH. So let's say hypothetically you get a pH of 1.85 on number 1. I'm just making up a number. Let's just say you get 1.85. So that 1 does not count as a significant digit. What counts as the significant digits are the 2 numbers to the right. So make sure on any pH that you have 2 digits, even if they're zeros, okay? Like let's say the pH worked out to be exactly 5. You need to write that as 5.00 because that's how every pH meter is going to read, is in decimal form with 2 places to the right. Now, when you get to question number 3, okay, because this is going to play out large later on. Same idea, hydrogen plus hydroxides yielding water, okay? So you got 2 millimoles of your acid, and you have 2.1 millimoles of your base. So now what's going to run out first is your acid. And you're going to have 0.1 millimoles of base that's left over, okay? So now it's a similar type idea, but it's kind of like the other side of the coin. Now you have excess base. Divide that by the total volume. That becomes the concentration of your hydroxide ions. Take the negative log of that. You get your POH. Subtract that from 14. So your answer to number 3 should be between 11 and 12. Okay? And hopefully that makes sense, because you're looking at them and, yeah, I've got more base left over. Yeah, my pH should be above 7. Okay. Now, when you get to number 4, okay? When you get to number 4, here's the fundamental difference that exists between what happened on 1, 2, and 3 and what's going to happen on number 4. First off, you have to look at what's structurally what's going to happen. So in number 4, you've got benzoic acid, and right away you see that it has a Ka value. So it's something that has a Ka value, right away, what do you know it is? Weak acid, strong acid? Weak. Kas only exist with weak acids. That's it, nothing else. Okay? Now, here's what's going to be different, even when you write this. So I've given you the full-blown equation. You can just write it as HA. But here's what I want you to see as a difference. If it's a weak acid, when you do that first reaction, you want to write it as the molecular form of that acid, okay? Because that's how it is existing. Is a little bit of it ionized? Yeah, maybe like 1 or 2%. But 97, 98% of this acid is going to be existing as that molecular form, not as the ionized form. So even when you write that first reaction, if it's a weak acid, you want to start with the molecular form of that acid. So that says, oh, okay, hey, Burkham, I understand what's going on. I get the picture. It's the molecular form. It's cool, right? Now, what's going to happen, we're going to form some water, and we'll have the anion. Now, here's what's important. When it's a weak acid, strong base titration, I very much worry about the anion concentration, okay? Because I have to have that anion concentration to figure out what the pH is going to be, because that's part of the Ka calculation, okay? If it's a strong acid, I could care less about what the chloride ion concentration is. It's just like talking with freshmen. Like, I could care less what your opinion is. It doesn't matter. This is all I hear, okay? It's not going to change anything. Now, but if it's an anion, which is the conjugate base off of weak acid, and again, here's the dichotomy. The weaker the acid, the stronger the conjugate base is, okay? And that's one of the things that you just need to think through. Oh, right. If it doesn't ionize very much, it's because there's a really, really strong bond, okay? That's it. So if you go to prom and you see how easily people ionize, that's a reflection of what's that dynamic between the two people. If they're like, oh, I love you, don't leave me, touch, so annoying, okay? But you got to figure, wow, that's a really, really strong bond versus, hey, you walk in the door, see ya, peace out, okay? Catch you on the other side, ready to leave. You got to figure that there's no bond between them, okay? And it's going to completely ionize. So here's what's going to happen. Because of the fact that this anion is the conjugate base off of a weak acid, it has the capacity to come up to that water and go, protons, give it up, baby, okay? The chloride won't do that, or any conjugate base off of a strong acid won't do it. But the conjugate base off of a weak acid will hold up the water molecule and go, give me one of your protons. Look, we have a hydroxide left over. Okay. So here's all you have to have for that reaction part of it. Boom. Ha plus O equals water plus Ha. Okay, that's all you need, right? If you really want to get technical and write out the full equation, you can. So here's your rice chart. Now, again, you can work in millimoles, you can work in moles. You can't work in molarity. Okay, that's the kicker. So if you do this, you got 15 millimoles of acid, you have 7.5 millimoles of your base, and since this is a non-buffered solution, we'll get into buffered solutions next week, that anion concentration is 0. Okay? Now, at this point, this is kind of cool. You go 7 minus 7.5 minus 7.5 plus 7.5. This becomes 7.5, mind that, 0, 7.5. Now, because of the fact that it is a weak acid, strong base, this thing is half neutralized. So when it's half neutralized, that's something special. Why? Your pH equals your pKa. But that is only when it's two conditions. When it's half neutralized and it's a weak acid. Okay? It's the only time it happens. It can't happen with strong acid because strong acid doesn't have a Ka value. Okay? It doesn't work that way. Can't do it with strong acid. Can do it with a weak acid. Can't do it with a strong acid. So, again, there's a couple of ways you can think this through. I care not. If you're old school, you can listen and go, well, Ka equals my hydronium ion concentration times my anion concentration divided by the concentration of my acid. And again, this makes so much more sense if you visualize what's happening at the molecular level of this reaction. Here's time. You have a very high concentration of the acid and you have no concentration of your anion. So as this reaction progresses, your anion concentration is going to go up, the concentration of your acid is going to go down. At some point, you're going to be half neutralized, and that's when your pH equals your pKa. Now, so if you're old school, you can go, oh, I need to solve for my hydronium ion concentration because I'm trying to find the pH, and I have to have my hydronium ion concentration. It's kind of cool. So you can look at this and go, oh, that's 7.5 millimoles divided by the total volume. And that's 7.5 millimoles divided by the total volume. Oh, those are the same. That goes away, which means my Ka equals my hydronium ion concentration. Okay, that's it. So then, if you take the negative log of both sides, your pKa equals your pH. Okay, so if you're a traditionalist, and you go, oh, Camp, president of the Ka club. It's cool, right? It's good for you. Your shirt has that on the back of it. Ka club, we rock, or we drop acid, whatever. And on the back, you've got that formula. People go, wow, nerd power, cool. All right. The beauty of it is if you wear that, you don't have to worry about going to prom. So, I'm just saying. Unless it's a fellow nerd, and then nerds of a feather flock together, I guess. Okay. So, if you're old school, okay, that's the more traditional understanding of how Ka works. Now, if you're new school, Burkamp, I got this Henderson-Hasselbeck equation. pH equals your pKa plus the log of your anion concentration divided by the concentration of your acid. It's cool. Anion concentration is the same as the concentration of your acid. You're taking the log of 1, which is 0, pH equals your pKa, boom, you're off to the races. Okay? Whichever one works for you. It's handy if you can understand both. Okay? It is, because that's going to lead you to a deeper understanding of this. Now, so your answer to, obviously, number 4 should start with a 4. Okay? Maybe 4.19, just saying. Now, when you get to number 5, okay? On number 5, pay attention that now we have a different acid. Okay? We have a completely different acid. Completely different. Okay? Now we have hypochlorous acid. Let's say hypothetically on the quiz tomorrow, I gave you benzoic acid, which has a Ka of 6.4 times 10 to the negative 5th, and I give you hypochlorous acid, which is 3.5 times 10 to the negative 8th, and ask you which one is the weaker acid, hypochlorous or benzoic. Which one is the weaker acid? Evan.
Hypochlorous.
Why?
Because it has a smaller Ka value.
So what?
Stronger acids have bigger Ka values.
Why?
Because that means a larger amount of them are getting dissociated.
Okay. That's what I want. Just don't tell me, well, the Ka value is bigger or smaller. So what? That's like saying it changes. Big whoop, okay? So look at how you calculate Ka. It's your hydroniums times your anions divided by the concentration of your acid. So the only way that you can make a smaller Ka value is if these numbers up on top are smaller. Okay, that's it. So the only way you can get smaller values of that is if it disassociates less and less and less and less and less. And again, here's the dichotomy. The weaker the acid, the stronger the bond with the conjugate base. It doesn't ionize much. Okay, that's why it doesn't dissociate very much. So if you take that anion though and you put it in water, it's going to give us a proton because it's such a weak acid, it has such a strong conjugate base. Okay, so here's the story on number 5. On number 5, notice that we have not added any hydroxide. Number 5 is just old school, find the pH. All this is HA, hydrogen plus your anion. There has been no hydroxide added. 0 zip. It's not a buffered solution. Your answer to number 5 should be a little bit bigger than your answer to number 4. Okay? A little bit bigger. Not much. A little bit bigger. Now, when you get to B, now we're going to start to add some base. So here's the difference in the two reactions. So on 5A, it's just the acid. And it's just ionizing. That's all it's doing. Okay? Do not put hydroxide ions in 5A because we haven't added any hydroxide yet. Okay? Don't worry about it. It's not there. Now, when you get to 5B, here's the difference. So on 5A, there's your action. On 5B, again, I'm going to write it as the molecular form because it's a very, very weak acid, and it's going to be existing as that molecular form, not ionized. Now I'm going to react with hydroniums. I'm going to get water and the anion. You have to see the difference in what's happening on 5A and what's happening on 5B. Okay? Hey, I'm adding hydroxides. Ooh, that's a new kicker. So the hydroxide is like the proton bully, much more a bully than the anion. The hydroxide walks up to the hydrogen and says, both guns, give us a proton. This has no chance, no chance. It is going to give up that proton because that hydroxide is such a strong acid. So you're going to form this water, and the anion is going to go, well, I guess I'll go out here and chill out by myself. Okay? So, on your rice chart, so you do this is like 1 millimole here, this is, I think, 4, and this is a non-buffered solution, so that's going to start at 0. You're going to go -1, +1, 0, 3, 1. Now, if you want to go Henderson-Hasselbalch, which I recommend, now, let's just talk about this before you do any calculations at all. So my anion concentration, technically, is going to be 1 millimole divided by the total volume of the solution. My Ha is going to be 3 millimoles divided by the total volume of the solution. But because you're dividing both by the total volume of the solution, do you really need to do that? No. Basically, you can take the log of 1/3. Now, step back, Jack, and look at the math of this for just a second. You're taking the log of a number less than 1. When you take the log of a number of less than 1, is that a positive or negative value?
Negative.
It's negative, right? So what that tells me is that my pH is going to be less than the pKa. Okay? Because what's happened here, again, understand what happens with concentrations. Oh, I'm starting with a high concentration of my acid, and the concentration of my anion is going to be at 0. Okay? So what that tells me is that I'm not even half neutralized. So what that tells me is that I'm in this region to the left of that half neutralization point. So I still have more acid than I do anions. And as long as I have a higher concentration of my acid than I do of my anions, my pH is going to be less than my pKa. At the equivalence point, that's like this teeter-totter. So if you're on that side, the teeter-totter is going to show that your pH is less than your pKa. At half neutralized, the teeter-totter is even, okay? pH is going to equal your pKa. Once you go past that point, then the teeter-totter is going to tilt, okay? And now it's going to go towards my anion side, and then my pH is going to be above my pKa value, okay? So your pKa value basically tells you where the balance point of this teeter-totter is. This tells you which side the teeter-totter is going to tilt to. Is it going to tilt towards the anion side, or is it going to tilt toward the molecular form of the acid? So if you like a visual, think of that, okay? So your answer to 5B should be around 7, okay? Now, when you get to C, okay, what's going to happen here on C is that you're going to, at this point, all of your hydroxide is going to be used up. You've got the 4 millimoles of this, so at this point, you're going to be half neutralized. pH is going to equal your pKa. Now, the kicker is going to happen when you get to E. Okay, so E is the most complicated one. On the quiz tomorrow, I'm not going to expect you to do something like E, okay, in any way, shape, or form. But I want to make sure and go through these steps, because this is on E is a multi-step process. And if you just memorize the steps, you're screwed. But if you understand why we do each step, then you're really going to understand what's going to take place. So when you get to E, HA plus OH yields water in your anion, okay? So you've got 4 millimoles of your acid, you have 4 millimoles of your base, you have no anions, -4, -4, +4, goose egg, 4 millimoles, okay? Now, if, this is a huge if this had been hydrochloric acid and sodium hydroxide or any strong acid and hydroxide, your pH at this point would just be 7 because of the fact that the anion would have no reaction back with the water. So if it's a strong acid, strong base, neutralization is 7 because there's no secondary reaction that takes place. The anion comes up to the water molecule and says, hey, let's just hang out. I really don't want your protons. Let's just chill, okay? And that's what happens. However, this is not the case. This anion is the conjugate base off of a weak acid. So now it turns into a bullet. And it goes up to the water molecule and says, give me one of your protons. The water says, fine, take one, whatever, chill, just be cool. Just take the proton and go away. Just leave me alone, okay? So what happens is that you're going to start a secondary reaction. That is not going to happen if it's a strong acid, okay? But it will happen with a weak acid. So at this point, there's a couple of things you need to do. You need to count it a second reaction, okay? Because if you don't know what the reaction is, you don't know what's going on. So what's going to happen is that now we're going to look at that anion reacting with the water to reform the acid and the hydroxide. So this is my new reaction. This is my new chart, okay? Now, we're not neutralizing anything. This is Mother Nature at this point is trying to find a new equilibrium, okay? There's no hydroxides involved, nothing. This just becomes its own entity again. So what that means is that now you have to go back to having molarity. Not millimoles, not moles. Now you have to have the molarity. To get that, you need to take that 4 millimoles and divide it by the total volume that you've added together at that point, which in that case is, what's total volume, 80? So you divide that by 80 milliliters, the milliliters cancel out, you get molarity. So that molarity is 5.00 times 10 to the minus second, okay? This is what you've got to be able to do on the quiz tomorrow. I'm going to give you a problem in just this part of the problem, okay? Not the full-blown thing, just this part of this. So tomorrow, if you don't do something like this, when you form hydroxides, you have done something horribly wrong, okay? I'm just telling you. If you hand in that test tomorrow, and you go, wow, I never found a hydroxide ion concentration, you have done something horribly, horribly wrong, okay? So you're going to go 0, 0, minus x, plus x, plus x. This becomes 5.00 times 10 to the minus second, x, x. Now, here is the KB kicker. This is acting as a base, so you have to use the KB value. But, do you have the KB value?
The Ka value.
No, but you have the Ka value. And knowing the Ka value, you can find the KB value. So, another step that you need to do is you realize KB is going to equal Ha times O divided by A, right? That's what you got. So, these are going to be your x squareds, okay? Your anion concentration is going to be 5.00 times 10 to the minus second. That Kb value is going to be the auto ionization constant of water divided by your Ka value. And again, here's the kicker. This is why you write out that reaction. So when you find X, you know what you're finding, okay? When you get that X, you go, oh, literally, oh, that's my hydroxide ion concentration, oh, okay? So when you find X, that's your hydroxide ion concentration. So Vanessa, then what are you going to do? Take the negative log of that, which is going to get you your
pH, or POH.
POH, and then what are you going to do?
Subtract that from 14.
And then you're going to get your pH. So your answer to E should be around 10. Okay? So this harkens back to a question that Evan asked about when we started the lab, and we were looking at the graphs. Okay? So if you look at a graph of pH versus volume, okay, and here's 7. So if it's a strong acid, and this is your volume of your base, if it's a strong acid, at the equilibrium point, that pH is going to be 7 because there's no secondary reaction that kicks in. Chlorines are there, nitrates, whatever they are, you're just not going to start a secondary reaction. They're going to leave the water alone. But if it's a weak acid, okay, and here's the kicker. There's a couple of ways you can tell if it's a weak acid. First off, the initial pH is going to be higher because it hasn't ionized as much. So if you have, like, say, for example, a 0.1 molar solution of hydrochloric acid and a 0.1 molar solution of acetic acid, the pHs are going to be vastly different. The pH of that hydrochloric acid is going to be much lower because you have a much higher concentration of hydronium ions. The pH of your acetic acid is going to be higher because it hasn't ionized very much. So the other thing that's going to happen is you neutralize it. What's going to happen if it's a weak acid, that equivalence point is going to be higher than 7. And the reason that it's higher than 7, or heaven, is the fact that you start a secondary reaction that generates hydroxides. So even though you've neutralized it, even though you can use MAVA equals MVVB, okay, you can use that same equation with a weak acid, strong acid, doesn't make any difference, because moles is going to cancel out moles, okay? So don't look at this and go, oh, if that only works with strong acids. No, it works for any acid, okay? It does, because you're neutralizing similar number of moles. So you can find molarity, volume, whatever. But here's what's going to be important. If it's a strong acid, you neutralize it, the pH is just 7, because there's no secondary reaction. If it's a weak acid, when you neutralize it, you start a secondary reaction that creates hydroxides, and that's why that pH is higher at that equivalence point. Okay? Does that answer that question, Evan?
Yeah.
Okay.
Theoretically, does the secondary reaction take place even if they're not neutralized fully? It's just so minor.
Yeah, it's always going to happen, but it's just like you're spitting in the ocean. Okay, it's going to be a drop in a huge bucket, which really isn't going to make any difference.
Okay.
Now, speaking of which, when you get to F, okay, so when you get to F, what you'll realize on F is that you have an excess amount of hydroxide ions, okay? Now, that source of those hydroxide ions comes from the fact that you have overloaded the solution with a strong base. So what's happening on F, okay, and here's the difference. And it's an order of magnitude. So this one, without any additional hydroxide ions, you are generating a very, 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 very tiny amount of hydroxides, okay, from that secondary reaction. But it's enough to boost the pH. What happens on F, okay, is that you do this, Ha plus OH yields water and the anions, okay? And in this situation, you have 4.5 millimoles of your base, you have 4 millimoles of your acid, you go -4, -4, 0.5 millimoles. So at this point, that is like the dominant source of your hydroxide ions. Is this reaction over here going to generate some hydroxide ions? Yes, but it is a drop in the bucket compared to the concentration that's going to come from this. So when you have that excess base, take that, divide it by the total volume, there's your concentration of your hydroxide ions, take the negative log of that. Don't worry about this. Is it going to happen? Yes. Is the amount that it's going to generate going to make any difference compared to this value? No, because it's literally an order of magnitude bigger in terms of this concentration of hydroxide ions. That's another reason you get such a big spike when you go past that equivalence point, because now that dominant source of your hydroxide ions is coming from that base. Okay? So your answer to F should be around 12. It's an ish, but it's around 12. Okay, how are you all feeling about this? Decent? Got it?
Yeah.
Okay. All right. So stop that. Okay, so this is what makes this assignment unique. Out of all the assignments I give in any classes, honors, chemistry, AP Physics 1, AP Physics 2, AP Chemistry, this is the only time I basically give this same set of calculations twice, because it is so vital. This is a situation where this just has to become automatic. So here's what I want, and here's the ZAC clause. So on number 1, you're going to do a titration with benzoic acid. Here's your Ka. Now, you obviously don't have room to do this here. I want this done on another sheet of paper. So you want just the initial pH, you haven't added any hydroxide. So then what you're going to do is basically, you're going to keep track of that pH. Imagine that you're doing a titration. you add 50. Then you're gonna add 100, then you're gonna add 150, then you're gonna add 200, then you're gonna add 400. And you're gonna calculate the pH at the end of each of those. Now, here's the ZAC clause. When you get past B, what you can do is go, here's my reaction, OH yielding water plus the anion. So after, what you can do is just write that at the top, and then basically kind of keep track of these columns as you go down. Okay, so in other words, you don't have to rewrite that reaction every time because it's going to stay the same. Now, with that caveat, okay, with a little bit of freedom also comes responsibility, is that if you're going to do this, okay, so let's say you're going to do B, so you're going to have a certain number of millimoles of your acid, boom, anion, change, boom. Then when you do C, leave me some kind of visual space that says, okay, now I'm doing my C calculations, okay? Then I'm doing my D calculations. So that way, when I'm looking at this, I have an idea of what I still have an idea of what you're doing, but you don't have to rewrite everything each time. Now, obviously, when you reach the point where it's completely neutralized, that's where I want to see like a separate set of calculations with that anion reacting with the water to reform the acid and the base. Now, when you get to number 2, 40 milliliters and your base. So what's different on number 2, why didn't I give you the Ka value? Because it's a strong acid, okay? It's a strong acid. Now, when you get to number 3, you're back to a weak acid, you have acetic acid, 0.1 molar. Notice on these numbers, if you look, you're going 50, 100, 150, 200, 250, okay? Similar type of things what's going to happen up there on number 1. Now, when you get to question number 4, you're going to look at your answers to 2D and your answers to 3E. Explain the differences in terms of the relative strength of the conjugate base resulting from the titration and the interaction with the water molecule. Okay? So help me God, if you just write, they're different, or it changes, Ema, I will flip out. Okay?
I'll find the synonyms. I'll pull up the synonyms.
For different than change.
The values are no longer the same.
Anyway, okay, I am done. Okay? So you have, if you haven't finished up the yellow sheet, get down for the yellow sheet. If you are done with that, get that handed in. And then you have the rest of the time to work on this. Yes? Yes.